Welcome to my presentation on subcode ensemble decoding of linear block codes. I gave this presentation at this year's ISIT in Ann Arbor. Now I'm happy to share with you my results. I want to start with a short motivation. For future applications, short block codes will become more and more important. For instance, if we consider scenarios where low latency is important, such as low latency applications in 6G or the communication of control commands, but also for setups like IoT, where we only have a very small payload that we want to transmit. Those are scenarios where we require short block length codes. However, if we now look at the performance between practical decoding schemes like belief propagation and successive cancellation decoding and optimal ML decoding, we often observe still a significant gap. So in this plot here we can see the performance of belief propagation decoding of the 5G LDPC code compared to ML decoding. So we see on the y-axis the frame error rate over the SNR, and at the target FER of 10 to the power minus 3 we can still observe a gap of more than 1 dB. And to reduce this gap, ensemble decoding schemes are a promising candidate because they promise to both improve the decoding performance, therefore reduce the gap, and at the same time reduce the decoding latency, which is important for many of these aforementioned scenarios. Before we go to subcode ensemble decoding, I want to give an intuition and understanding on how the different ensemble decoding schemes work. All ensemble decoding schemes are defined by running multiple decodings in parallel. And the idea is to exploit so-called diverse decoding regions of different suboptimal decodings. So in this setup that we see here, we assume that we transmitted an all-zero code word, which is this red dot, and we received Y at a receiver. And the green regions are now those so-called decoding regions, which is the set of all received words that are correctly decoded on the all-zero code word in that path. And therefore, if we use multiple different suboptimal decodings, each with a different decoding region, we can exploit diversity, because if one path succeeds to decode it can correctly decode when another path potentially fails. However, after those parallel decodings, we have to decide which estimate we want to use. And for this, we use the so-called ML in the list rule to simply choose the candidate that maximizes the likelihood. And in the paper by Krieg et al., they broadly categorized existing ensemble decoding schemes into two classes, which we are going to analyze on the next slides. On the first side, on the one hand, we have the ensemble decoding schemes that alter the graph representation. One very known example for this is multiple basis belief propagation decoding, which uses redundant parity check matrices for BP decoding in each pass. So from now on, we are mostly considering BP decoding. And by using different redundant parity check matrices, the decoding region of each pass might look different, and therefore we can have a decoding gain and use multiple to improve decoding performance. However, there's a drawback, because it's rather difficult to find good redundant parity check matrices, because parity check matrices that are suitable for BP decoding must be sparse, and therefore we have to find low-weight dual code words, which is not an easy task, and therefore this is a limiting factor, in particular if we go to medium block lengths like above 128 to 512. And an alternative approach, so on the other side, we have the ensemble decoding schemes that alter the noise representation. One known example for this is automorphism ensemble decoding, which uses knowledge of the automorphism group of the code. An automorphism is a permutation that maps the code space again onto itself. And now if we sample such an automorphism and apply it to our received word y, we can map it potentially into a decoding region. So in this setup now, we have the same BP decoding in each pass, therefore a different shaped decoding region, but by applying this permutation, we rotate somewhat the decoding region, and therefore by altering this noise representation, we map it onto this shifted or rotated decoding region, and this potentially generates diversity which we can exploit to improve decoding performance. But also automorphism ensemble decoding has some drawbacks. For instance, it requires the knowledge of the automorphism group, which is not always available. And there exists also cases where the symmetry of decoding potentially absorbs the effect of automorphisms. This is an effect that was observed for quasi-cyclic LDPC codes with BP decoding, but also for successive cancellation decoding of polar codes, and therefore sometimes limits the application of AED. Now, because we are interested in defining subcode ensemble decoding, we first have to take a look at what are linear subcodes. And in our work, we define a linear subcode to be a k-prime dimensional subspace of our original code. So we assume that our subcode is again a subspace, therefore again a linear code. So here we have a simple illustration. We have the original code C, and our subcode CS contains code words that are also elements of C, but it doesn't contain all the code words from the original code. Therefore CS is a subset of the original code, but due to the condition that it is a subspace, it again fulfills some structural properties. And so linear subcodes are again linear codes, which sometimes is nice to describe them using parity check matrix, generator matrix, for instance. But another nice property of subcodes is that their minimum Hamming distance is lower bounded by the Hamming distance of the original code. And this gives us a motivation why we want to use subcodes for subcode ensemble decoding. Because if we have a larger minimum Hamming distance, we have improved error correction capabilities that we might exploit for ensemble decoding. So the idea that we are going to take a look at is to exploit diverse decoding regions of the subcode decodings to constitute ensemble decoding. And for this, because we are mostly interested in this work on BP-based decoding, we require to find a parity check matrices of subcodes which are suitable for BP decoding. And now we ask ourselves, given the parity check matrix of our original code, how can we find the parity check matrix of a linear subcode? And given this parity check matrix H of the original code, it is very simple to find the parity check matrix of a subcode by simply appending a row HL, which is linearly independent of the rows of H. And then if we append HL to H, we obtain a new parity check matrix HL with an increased rank, and therefore we can check that this is a parity check matrix of a linear subcode. If we append a single row, it's a k-1 dimensional subspace of our previous code. Later, when we are going to look at ensemble decoding, we are interested in something called a linear covering. A linear covering is a set of linear subcodes or subspaces in mass of our original vector space or code, such that their union jointly covers the original code. And this is going to be important for ensemble decoding, because if we do not fulfill this property, we are not able to decode an arbitrarily transmitted code word. So one interesting question from a mathematical perspective is how many subcodes are required to possibly cover the original code. And this is something called covering number. So this question, how many do we need to cover this quantity, this number, how many are required, is called a covering number. And in this illustration here, I'm first going to show why two codes are not, or two linear subcodes are not sufficient if we consider an original code being a binary code. So again, we have our point space here of our original code on the left-hand side. And again, red is the all zero code word. And now we separate this code space into two subcodes, CS1 and CS2. And because they are again linear subcodes, both contain the all zero code word. Now, because we assume that we have a binary code and we form a k-1 dimensional subspace, both CS1 and CS2 will exactly contain half the number of code words as the original code word. And therefore, it is guaranteed that if we take their union, there will be at least one code word that is not in the union of the two subcodes. In the paper, we do it a bit more formally, and there we can already see that there's even more code words that are not covered by the subcodes. But this illustration here already gives a good incentive why the covering number, therefore the number of subcodes required to cover the original code, must be larger than 2. However, we are lucky. We can say that the covering number is going to be 3, and therefore 3 subcodes, which are k-1 dimensional, suffice to jointly cover the original code. So in the illustration, the orange code word was not covered by CS1 nor CS2. However, if we design CS3 suitably, then their union jointly covers the original code. And to state this a bit more formally, it is known from the reference that at least 3 linear subcodes are required to cover the original code. But we are a bit more interested not in only having this covering number, but being a bit more practical and require a construction. So we are interested in, if we are given 2 distinct subcodes, CS1 and CS2, which here are k-1 dimensional, we want to find a non-trivial H3 such that the subcode defined by appending H3 to the parity check matrix constitutes a linear covering together with CS1 and CS2. In particular, we are interested in non-trivial H3, so H3 not being the all zero row, because if we use H3 being all zero, we do not change the decoding behavior compared to H, because an all zero row does not change the behavior. And therefore, we are interested in finding a non-trivial H3. And now if we assume that the parity check matrix of the subcodes CS1 and CS2 are constructed by simply appending rows H1 and H2 to H respectively, then we can find this non-trivial row H3 to be the linear combination of H2 and H1. And then by appending H3 to our original parity check matrix, we can find a subcode, which is not necessarily in this case a proper subcode, but for us important is that H3 is non-trivial, such that CS1, CS2 and CS3 jointly cover the original code. With this at hand, we can now formally take a look at subcode ensemble decoding. The idea is to select M parity check matrices such that those parity check matrices constitute linear subcodes of our original code and use those parity check matrices to constitute paths of subcode ensemble decoding. So here we can see the full scheme. It's very similar to multiple basis belief propagation decoding, but an important difference is that we allow to append linearly independent rows and therefore to use subcode decodings. And as I already mentioned earlier, not all paths can decode all code words, since it might be that we transmit a code word from our original code C, which is not contained in one of the subcodes. However, if the subcodes constitute a linear covering, we can guarantee that at least one path is has at least the capability of potentially decoding this code word. So, important take-home message, the subcode should constitute a linear covering. If we now take a more practical look at this, the question is, how can we construct an efficient ensemble? And that one practical approach to already fulfill this linear covering by construction is to only choose H2 until HM to be potentially parity check matrices of a subcode, and keep H1 fixed to be the original parity check matrix. So the original code is also a subcode of itself, just without using the dimension. So this also matches the definition of the subcode ensemble decoding we proposed before. However, if we choose H1 equals H, we are guaranteed to constitute a linear covering. And in particular for BP-based decoding, to use H is often beneficial, but because if we take a look at LDPC codes, the original parity check matrix already yields very good performance, and now the goal is to choose this other path to further improve the decoding performance. And in particular, if we take a look at LDPC codes, which we are going to look at in this work, the idea is that we also want to exploit this good structure of H when constructing the parity check matrices of our subcodes. And it's very easy to generate subcode PCMs by simply appending a single linearly independent row to H. To be precise, we are not really required that those rows are linearly independent, but there exist many more rows that are linearly independent. So if we arbitrarily sample a row, it is more likely to be linearly independent to the rows of H than linearly independent for the codes that we consider. And therefore, typically, if we just sample a row, it will be linearly independent and constitute the parity check matrix of a linear subcode. And one approach, or we are going to compare two approaches. One is a rather natural idea or more intuitive idea. Is that each code word should be protected by at least one of the auxiliary paths. So in this idea, in this approach, we want to choose, for instance, the auxiliary paths, so H2 to HM, such that they as well constitute a linear covering, such that we have a more equal protection of all code word. However, here we face the drawback that due to theorem 1, H3 is a superposition of H1 and H2. And if we choose H1 and H2 to be sparse, which is good for BP decoding, H3 is more likely not going to be sparse. And therefore the third path or the third auxiliary path will have degraded decoding performance. And in fact, this trade-off showed us that a more greedy approach is indeed often beneficial. Here we construct a very large set of K much larger M candidate paths, and then, as described in the paper, we use some greedy algorithms to choose M-1 paths that correctly decode as many received words as possible that the original BP decoding cannot correctly decode. So we precisely try to choose our auxiliary paths such that they enhance the standalone decoding. And as I already indicated a bit, but was somewhat surprising to me, the greedy algorithm typically yields better performing ensembles, even though some code words are potentially not contained in any of the subcodes of the auxiliary path, but only protected by the very first pass. This was a bit surprising to me due to some symmetry reasons. However, I think the reason for that is that we have, due to theorem 1, the superposition which degrades the performance of that path. And this is the take-home message here. BP is suboptimal. Sometimes the structure of the tenor graph is more relevant than equally protecting all code words. Now I want to give a short comparison and also give the parameters and the codes that we used for our simulations. First, I want to compare subcode ensemble decoding with other ensemble decoding schemes, namely MBBP and AED. In contrast to MBP, we can construct paths without having an exhaustive search for low-weight dual code words. This is a very limiting problem for MBBP if we want to apply it to longer codes. And for SCD, because we can simply generate linearly independent rows without having to check that they are low-weight dual code words, because they are, in fact, when they are linearly independent, no code words of the dual code, we can generate many rows that we can test and check how we can improve the decoding performance. Also, if we now compare to AED, we have no constraints on the symmetry of the decoding. So, for instance, for quasi-cyclic codes, the quasi-cyclic automorphism group is only usable with some additional tricks that are discussed also in the reference. However, with SCD, we are not limited or not constrained by some symmetry problems. And furthermore, for AED to be usable, we must know the automorphism group of the code, which is not always given. And in particular, to show the benefits compared to AED, we will consider the 5G LDPC code, which is a quasi-cyclic LDPC code. So using some tricks, as discussed in the reference, we can use the automorphisms there to improve decoding. So we will compare to SCD to AED for this code, but we will also consider irregular PEG code from the homepage from BK, where the automorphism group is unknown. Therefore, there AED is not applicable, and also this is a bit longer code, so there MBBP is also difficult to apply. And also, just for the simulation, each pass of all ensemble decoding schemes perform a maximum of 32 iterations, and we consider both sum product algorithm as well as the min-sum algorithm, and we perform Monte Carlo simulations using a binary input AWGN channel. So now I want to come to the simulation results. So here we can see on the y-axis the frame error rate over the B over N0 for the 5G LDPC code. We can see in orange the performance of min-sum algorithm performing 32 iterations and the performance of min-sum performing a maximum of 352 iterations. And in black again we can see the performance of the maximum likelihood decoding. So orange and black are the two lines that we know from the motivation slide. If we increase the number of iterations, we can improve a bit. And now if we depict the performance of AED as implemented in the reference, we can see that using AED with 11 paths, we can match the performance of equal complexity min-sum. So the red curve has a total of 352 maximum number of iterations. If we now count for AED, each pass uses 32 iterations. 11 times 32, we obtain 352. So green and red have the same worst case complexity, and green and yellow have the same worst case latency, because in AED, because it's an ensemble decoding scheme, all paths can be executed in parallel, and therefore if we have the same highest number of iteration in each path compared to the standalone decoder, then we have this approximately the same latency. And therefore it's nice because AED for a fixed latency, fixed complexity can yield the higher, the same performance with a reduced latency. But now if we take a look at SCD, we can even improve. So we can, for a fixed complexity, improve the decoding performance compared to the MinSum with 352 maximum iterations and AED. And what we can also provide with this greedy algorithm, it's a good intuition on how many paths we can use to still improve the decoding performance. This is discussed a bit more detail in the paper, but this is how we came up with this number 43. So this is something given from our analysis, a good choice, or the choice. If we further increase the number of paths, we do not expect much more improvement, but this shows that STD can reduce the gap to ML at a frame rate of 10 to the power of -3 to 0.8 dB. And importantly, we can outperform here the equal complexity, equal latency. So a very similar setup, AED using STD with the same number of paths. And now we are going to consider the irregular peg code. Now we see on the left hand side the performance using MinSum algorithm, on the right hand side here the performance using some product algorithm. In this case the automorphism group is unknown, therefore AED is not applicable. However, both for MinSum and SPA we can use SCD, subcode ensemble decoding, and in both cases for MinSum and SPA subcode ensemble decoding is able to improve the decoding performance compared to the standalone decoding. This now brings me to my conclusion. So in this work we proposed subcode ensemble decoding, which uses an ensemble of decodings on subcodes. In the case of BP-based subcode ensemble decoding, we can obtain a linearly parity check matrix of a subcode by appending a linearly independent row to our original parity check matrix. So in the cases of LDPC codes, this is a very sensible approach because we maintain the good structure of the design parity check matrix also when designing the parity check matrices of our subcodes. However, it's important to ensure linear covering. A very practical approach hereby is to simply set the first parity check matrix to be equal to the original parity check matrix, and then try to identify some auxiliary paths that can improve the decoding performance compared to the standalone decoding. And for this we can use this greedy algorithm, which is discussed with in more detail in the paper. And as we also discussed, subcode ensemble decoding can overcome some limitation of MBBP and AED. To rename them once more, compared to MBBP, we do not have this exhaustive search for low-weight dual code words, and in contrast to AED, we do not require knowledge of the automorphism group, and we are also not limited, potentially limited by symmetries of the decoding. So here you can find the paper of this talk, but I'm also very pleased to inform you that we applied subcode ensemble decodings to polar codes, which you can find in this paper, and this paper was also accepted for presentation at ISTC, and therefore you will soon get another video on subcode ensemble decoding of polar codes. So thank you very much for your attention. If you have any questions, leave them in the comment section or just write me an email, and yeah, thank you for your attention.